Hello, today we will look at my Y86 implementation for CSCE 312. We will look at it module by module, and we will start with the fetch module. The fetch module will seek through 10 bytes of instructions and push those onto the stack. When the 10th byte is on the last position on the stack, we will then receive a instruction code and the requisite val_c function register A and B, depending on what the instruction is. So the next thing to look at is the pipeline controller. So on the left side, this is where we control the logic for writing to the instruction cache. So we will wait 10 clock cycles, and then we will write this fetch cache, which is here. These are all the things that we write to the cache. And then, depending on what the instruction is, we will then begin a control sequence for the other caches and the other modules that we will write to. So let's look at the first module, which is the decode module. This decode module, very simple. It takes in register A and register B, and depending on the instruction, it will either retrieve those registers from the register file, or if the instruction has RSP, then we will just retrieve 4. 4 is the RSP register. So this decode sends RA out and RB out to the register file, and the register file will then write those back to the decode cache, which is right here. The next module is the execute module, and this simply takes val_b and val_c, val_a, and depending on the instruction, computes val_e, or sets the condition code, which we then use for the conditional jumps and conditional moves. We then write this result, val_e, and the condition code to the execute cache, pipeline cache. The next module is the memory module, and here I need to point something out a little quirky about this design, is that I have 2 identical copies of the same memory. I have a memory module here, which contains the memory of the program, and I contain one in fetch, and I upload the same code to both of these. I have them separated for convenience. I thought it would be kind of messy to have multiple things trying to access this one memory cell, and to keep things properly segregated. So this works as a fine solution. So depending on the instruction, we will read or write a particular value of program memory, or of the stack. So stack read and writes would occur in this memory module. They contain identical code when I upload them, but this is the memory module that will contain the changes. We then write the results of val_m to the memory cache. And the next module is the write back module, and this will take these values on the left, and depending on the instruction, we'll write back to a particular register. There is a bit of extra logic here to deal with a special case of the pop instruction, where we have to write 2 values. The register file is constructed in such a way where you can only write 1 register per clock cycle. So this necessitates that we need at least 2 clock cycles for this module. And we will discuss the clock cycles for these modules in just a second. The next module is the program counter module, where depending on the instruction, most of the time we're just going to val_p, which is computed in the fetch module, but occasionally we need to set the next program counter to something else, val_m, val_c. Okay. So the fetch module needs 10 clock cycles. That's over here to the left. The decode module needs 1 clock cycle. Execute needs 2 clock cycles. Memory needs 1 clock cycles, write back needs 2 clock cycles, 2 for that special case, and the program counter needs 0 clock cycles. So let's upload the code that was given in the lab that we were required to translate to Y86 assembly, and we will see what happens. So I'll upload it to fetch, and I'll upload a identical copy to memory. And now we'll observe the contents of this memory. What this program will do is we have an array of 8 integers here. They're all 1. And this program will write to the first half of this array and increase them by 1. So we should see half of these become 2, and the other half will remain as 1. So we will go here, we'll reset, and we will select a high frequency. We'll run it. Maybe a bit faster. I want to wait forever. Okay. So we got a halt signal, and now we will go check our memory module. See if what we wanted to happen did happen, and it did. Half of these integers in this array became 2, and the other half remained 1. So that concludes our discussion of this project.